Okay, like I had said before, when you get an angle that's bigger than 90 degrees, so like such as this 120-degree angle here, and you're left thinking like, well, what is the opposite side? What is the adjacent side here? And I pointed out that what you really want to think about is the right triangle that is formed with the x-axis. Um, in the book, they kind of go into that, and they use a different way of saying that, but it's basically the same point. But we'll go through and see what they're saying. They say for a non-quadrantal angle theta in standard position, its reference angle is the acute angle theta prime formed by the terminal side and the x-axis. Okay, so they're saying that the reference angle, so for like 120, for example, is the angle formed by the terminal side. So, um, that little hypotenuse guy there, the terminal side, and the x-axis. So here, this part would be your reference angle. Now we can see that that is going to be 60 degrees, right? This whole thing across would be 180. So that's 120 plus 60 to get there. Now, they give some rules here. I don't think these are too terribly important to kind of memorize, but we can kind of go through and say what each of them are saying for a moment. If you're in quadrant 1, so if you're already up here, then you don't need to do anything to get to a special reference angle to think about because you're already in the right place. If you're in quadrant 2, up in the top left, like a 120-degree angle, then you can get your reference angle by doing 180 minus your angle. That's basically what we just did a moment ago. We said we have 180, we take away that 120, and what's left is 60 degrees. So this is our reference angle, a 60-degree angle. For quadrant 3, they're going to say to get your reference angle, take your angle and take away 180. So like basically pull it back by 180 degrees. And once again, that will give you your reference angle, which in this image would be like that portion right there. One there. For quadrant 4, we would take our angle we would get our reference angle by taking 360 degrees and subtracting off the angle we were given. So if I had a 300-degree angle, then the reference angle would be found by taking 360 all the way around and taking away this piece, leaving you what you have left. Um, all these examples, I use the same number. Got a 60 each time. That wouldn't be the case all the time. It says or over here, so it'll say pi minus theta, theta minus pi, 2 pi minus theta. So just remember that these are in radians. So this is 2 pi radians versus 360 degrees. This is pi radians versus 180 degrees. Okay, so they're basically, I think this way of phrasing it is much less intuitive than just sort of looking at this image and understanding that we want to deal with the right triangle that is formed using the x-axis as one of its sides. I think that's kind of a much simpler way to summarize it. But since this is how the book says it, and the next examples kind of use that terminology, I wanted to go over that real quick. Okay, second thing here. There's a lot of information in the book that they list that I find a little bit. It's a little bit much to me. So, for example, they kind of give you this little cheat sheet that says like if you have an angle in quadrant 1, the sine of that angle will be positive, the cosecant will be positive, the cosine will be positive, the secant will be positive, the tangent will be positive, the cotangent will be positive. They go through these and they kind of tell you what to expect. So if you're in quadrant 2, you're expecting your cosine and your secant to be negative. Now, this is a lot of stuff to memorize. And once again, once we get more comfortable with this thing, the unit circle, I want to remind you why this is called the unit circle. This is specifically a circle with a radius of 1. So this gray line is always a distance of 1. The hypotenuse is always 1. When you have the hypotenuse being 1, think about what that means for your trig ratios. So if sine, for example, is opposite over hypotenuse, well, in this case, the opposite is just the length of that green line. So at 30 degrees, the sine of 30 degrees is just going to be the green line, 0.5, divided by the hypotenuse of 1. So the dividing by the hypotenuse part doesn't really matter. So what's nice about this unit circle is that sine and cosine, like your answer, so the sine of 30 degrees is just the length of this green line below my mouse. So the sine of 50 degrees would be 0.766. The sine of 70 degrees would be 0.94. And you can start to see this thing where those sine values, they start at 0, they go up to 1, they go down to 0 again, they go to -1. Excuse me, sorry. They go to -1, they go back to 0. So our sine value is the size of my green line, my cosine is the value of the blue line. So when you do this, you can start to get a sense of like, okay, yeah, so quadrant 1, sine should be positive. My green value is positive here. Quadrant 2, the same. Quadrant 3, sine should be negative. Quadrant 4, sine should be negative. If I look at my blue line around the circle, then I expect my cosine to be positive in quadrant 1, negative in quadrant 2, negative in quadrant 3, and positive in quadrant 4. Okay, so that is kind of what's being summarized here. I always think that math manipulatives that actually let you manipulate things, see how things change as you go, are much easier to understand than just like lists of answers. Same thing here. It says it may be helpful to memorize the trigonometric values for these special angles. I would say it's not going to be helpful. Um, were you to memorize all these, yes, you could kind of jump to things quicker. However, I think what's much better is to just memorize where we get all of these from. And it's really from just one thing. It's from an equilateral triangle. So as long as you know that you can start with an equilateral triangle, you can get quite far. So, for example, in this triangle, we have 3 equal sides, we have 3 equal angles. So those 3 angles have to add up to 180. That's just a truth statement about any triangle. But for an equilateral triangle, that 180 is going to be divided by 60, 60, 60. Okay, so if we have an equilateral triangle, we'll say that this is some length, this is the same length, this is the same length. Okay, so if we want to get a triangle that has 60 degrees and 30 degrees in it, all we have to do is split that split that equilateral triangle down the center. So we're going to split it down the center. Top angle will become 30 degrees. Bottom left will stay 60. We'll still have x here. We will have x over 2 right here. And if we use Pythagorean theorem, we can find our missing side. So for example, we would say that x over 2 squared plus something else squared, I'll call it b for now, equals x squared. Okay, well, I'm going to get x squared over 4 plus b squared equals x squared. Okay, if I try to rearrange this solving for that unknown b side, which I'm trying to figure out right now, then we could do x squared over 4 minus x squared. And I'm going to put this into the same fraction. So I'm going to call that minus 4x squared over 4. And that should equal, well, I guess that would be negative b squared. Sorry, let me move the other one over. Let's say b squared equals x squared minus x squared over 4. And then let's turn this one into the same denominator by doing 4x squared over 4. Okay, so now we get b squared equals 3x squareds over 4. And if I want to take the square root of that, that would give me b equals square root of 3x over 2. Okay, so the x's will kind of cancel out. So if I wanted to, let me put that in, square root of 3x over 2. If I want to just set x equal to 1 right now, then you'd see that the general ratio of a 30, 60, 90 triangle is you have the side length of 1, 1/2, and root 3 over 2. So now let's go through our different things for the 30 degrees. Well, the sine of 30 should be the opposite over hypotenuse. So 1/2 divided by 1, yes. Cosine should be adjacent over the hypotenuse. Well, you divide by 1/2, that cancels out the 2 on the bottom. Sorry, does it? Adjacent over hypotenuse, never mind. Adjacent over hypotenuse, so you get root 3 over 2. Tangent should be your opposite over your adjacent, so 1/2 divided by this. If I'm dividing by this fraction, I can flip it over and multiply. Opposite over adjacent. And let's write that one out because that one's not super obvious. So opposite would be 1/2 divided by adjacent. I'm going to flip over the fraction and multiply. So the adjacent's here. If I flip it, I'll get 2 over root 3. That'll give me 1 over root 3. Now they write it as root 3 over 3 because they've rationalized the denominator. They've multiplied by root 3 over root 3 to get root 3 over 3. Okay, so any of these with 30 degrees, any of these with 60 degrees come from taking a equilateral triangle, splitting it in half, and solving for your unknown side. Okay, so you don't need to remember 1, 2, 3. You don't need to remember 18 things. You just need to remember 3 steps. Take an equilateral triangle, split it in half, solve for that unknown side. You can go from there to figure out what all these values should be. For a 45-degree one, well, let's draw out a 45-degree triangle. We'll see a very similar thing go down. So with a 45-degree triangle, what you will get is, well, if it's a right triangle, first of all, and we have 90 here, 45 here, that means we also would have 45 here. So that makes it that whatever this length is will be the same as this one. Rather than doing x and having to cancel that out later, I'm just going to put in a 1 for now. So we'll say 1, 1. Well, that means that our hypotenuse should be the square root of 2, right? 1 squared plus 1 squared, we'd add those together, and we'd get 2, and then we'd take the square root to find that value. So if we want the sine of 45, that's going to be the opposite over hypotenuse, 1 over the square root of 2. They've rationalized it. Cosine will be the same. Tangent will be opposite over adjacent, so it'll just be 1. Okay, so any of this stuff, they say special angles. When they say special angles, they just mean that like these are particular angles that create pretty small values here, so they're not hard to memorize after you've worked with them a lot. And that's why on the unit circle, for example, we see 30, 45, and 60 show up on there. And if I like go to radians, we don't do 30, 60, 45. We do pi over 6, pi over 4, pi over 3. These are special ones just because they're really simple values to get to, starting with like just your standard equilateral triangle. Now, other angles will be formed by other triangles, and those ones, like if I had 41 degrees or something, those ones will not be as easy to figure out, what should be all the relationships. So anyways, we call equilateral triangles. So 60, 60, 60, we call 30, 60, 90 when we split that equilateral in half, and we call 45, 45, 90. These three are what's known in geometry as special triangles. These two as special right triangles. Okay. And I think that is it for that little section. Yes, it is. Okay.